Today's lesson will be about involving multiple functions and ways that we can work with multiple functions, including composition and inverse of functions. We'll start with composition. Functions can be combined by adding, subtracting, multiplying, or dividing, or composing. For the most part, you'll remember adding, subtracting, multiplying, or dividing. Those involve combining like terms and operations with polynomials, which you spend a lot of time on. Composition is probably the newer of those operations that you can do with functions, so we'll review composition a bit for today. Also a little bit of algebra in today. So here we have an example of two functions, one exponential and one rational function. We're being asked to find f of g of x. So what I think then, when I start to work on this problem, so I think f of g of x is 3 divided by 2x minus 1. And then if I want to find f of 3 divided by 2x minus 1, then I'm going to go to the function that is f. X on the left has been replaced by the rational function, so I'm going to replace the x on the right with that same polynomial function. And I can simplify, but only a little, and there's my composed function. Remember, when you're multiplying here, it's like multiplying 2 over 1 times 3 over 2x minus 1, so that gives us 6 over 2x minus 1. The next question does not involve a composition. It's just the x values for which f of x equals 5. This is just a little algebra review. So 5 equals e to the 2x. And then remember that your tool for solving an exponential function, especially one involving e, is natural log. So I'm going to apply the natural log, or take the natural log of both sides. One of the properties of logarithms is that if I have a logarithm of a function that involves an exponent, I can bring the exponent down front. So I have natural log of 5 equals 2x times the natural log of e. And then remember from your pre-cal background that the natural log of e is 1. And so I can complete my solving for x there. Natural log of 5 divided by 2 equals x. We'll leave our solution in this format. There's no need to change it to a decimal. In fact, this answer is more exact. We do a good bit of non-calculator work, and when we're working non-calculator, we just leave solutions looking like that. What is the range of f of x? So in order to answer this question, I have to remember yesterday's lesson about graph shapes. And I remember that f of x is an exponential function, and exponential functions look like that, increase to the right, with an increasing exponential function. I remember that there's an asymptote at 0. So the range of f of x is 0 to infinity. Notice the 0 is not included because 0 is an asymptote, and then it grows to infinity. There was no work to be done with that. That's just another way of checking, do you know your basic graph shapes? The domain of g of x, this is an older question as well. Remember that g of x is a rational function, and the error zone with rational functions is that we can't divide by 0. So we just write that, I can't divide by 0. And then continuing on, solving for x, x can't be 1/2. Can leave it in that format, or I can write it in interval notation. Interval notation is much more complicated at this point. And there we have it. The second graph that we have here, composition of functions from a graph. And so just kind of thinking through how we deal with this graphically. If we're asked to find g of f of 0, the first thing we do is find f of 0. F is the red graph. So f of 0 is 2. 3 right there is f of 0. So then I'm finding g of 3, working inside out. G is the blue graph. G of 3, 1, 2, 3 is 1, 2, 3, 4. And there's my solution. If I want to find f of g of 2, I just do the opposite. I find g of 2 first. G of 2 is 1. So then I'm finding f of 1, and f of 1 is 0. And there's my solution. For where f of x equals g of x, I'm looking for points of intersection on the two graphs, the x values for the points of intersection on the two graphs. So I have f of x equal to g of x at x equals 1, and at x equals -1. Our next example involves reading data from a table. This is not complex, but it can be confusing if you've not looked at a table of values in this way before. So a little example here. F of -1, I just find x is -1 here, f of -1 there, f of -1 is 3. G of x equals 5, so I'm reading on the line of g of x for where y is 5. I'm here. So there's where g of x equals 5. The x value where that occurs is 5. Finding f of g of 3, I'm going to read the table starting at 3. G of 3 is 0. So then I want to find f of 0. So I come back near on like this, and then f of 0 is 5. If I want g of f of 0, I start with f of 0. F of 0 is 5. And then I'm finding g of 5, and g of 5 is 5. Then the last thing for today is just a reminder about inverse functions. We are not going to spend a lot of time finding inverse functions, but you do need to remember that inverse functions reverse x and y. So if f of x equals y, then f inverse of y equals x. The independent and dependent variables exchange places. That also happens with the ordered pairs on the graph. So if the ordered pair 3, 2 is on the graph of G, then the ordered pair 2, 3 is on the graph of its inverse. The confusion with inverse functions really rests with the notation. You're supposed to know that f inverse indicates that x and y are switched, but the notation involves x as the input variable for both f and f inverse. So don't let the use of x in both cases mislead you. You know that if it's f of x equals y, then it's f inverse of y equals x. That's it for today.